All right, let's have a look. So, simple machine problem. Okay, so man slides 24 camera. Okay, so they're telling us the mass of the object that's being slid up the ramp, telling us the length of the ramp, height of the ramp, and the efficiency. So you're supposed to determine what's the force with which he's got to push to get this thing up the ramp. So what are you gonna do? What are the important? Let's write down any important equations here. What can you tell me about ramps, inclined planes? What's the theoretical mechanical advantage or ideal mechanical advantage?
Distance, so length over height.
Length over height. Okay, so L over H, and we have that, right? That's 11.9 meters over 2.08 meters, which is something. Okay, what else do we know? What about actual mechanical advantage? Okay, so that's going to be, which one's on top? That'd be output, right? Because if the mechanical advantage is bigger than 1, it's multiplying force, right? So we've got output force over input force. We're trying to find input force. What about efficiency?
Actual over theoretical.
Okay, so one way to do it is actual over theoretical mechanical advantage. What's another way?
Using work.
Work. So it's going to be, so which one over which? Which one's going to make sense? What's the biggest efficiency you can get? 1, right? So it's got to be a maximum of 1. Okay, so output over input. Yeah, output over input. Yep. Right? Because output can be less than input, but you can't get more work out than you put in. Yeah. Here, just fill that out. Okay, so, all right, so then what are we going to do? We're trying to solve for, and what's work, by the way? Force times distance, right? Okay. Force times distance times the cosine of the angle between. But for something like this, the work, we don't really have any angles, do we? Input work is when we're pushing up the ramp, right? So it's just force times length of the ramp. There you go. And output work would just be what's accomplishing. So it's going to be lifting it up, right? So weight times height, right? Okay, so output work we said was, we'll use this one, won't we? Right, this will probably be a little bit easier. So output work is going to be weight, which is mg, right? Times how far that weight is moved vertically, so times height. Input work is going to be
The length of the ramp.
okay, times
Force
input force. Good, so input force times L. And that's our unknown, right? We know the efficiency. What's the efficiency? 0.645. So there's our equation, isn't it? That's the equation we want to use because it's only got one unknown. I can plug in M, G, H, and L, and all I'm missing is the input force. Right? Okay. So we could, if we wanted to, we could just exchange diagonally, I guess. We want to do this real quick. And we'd end up with input force equals, in my ratio, I've got MGH. So what are those things? Well, we'll plug them in for a second. MGH over efficiency, which I'm just going to call E times L, right? Now I can just plug and chug. Cheer, cheer. Okay. Make sense?
That's E.
Efficiency. Which they give us, the efficiency is 0.645. They give it to us as a percentage. But we of course, we want to use a decimal. All right? Make sense? Okay. We left off yesterday. We had just done the screw or the jack screw, right? And so we had decided, right, we had done a let's do a more realistic calculation. So if you're gonna do like the threads on an actual screw, not just for fine tuning, but for, somebody look up, what's a fine thread count on a machined screw?
108.
108?
508.
No,
508 seems like that's a little too fine.
Me too. It's
Yeah.
pretty fine, but it exists. That's why.
not for actually screwing things together.
But that's just for really fine adjustments, right? But if we want to actually pull something together, we need, and you see what the problem would be. If you look at the cross-section of a screw, what's it look like? It's gonna look like, you know, there's the core, right? And then it's gonna look like that, right? They're gonna be sort of triangular cross-sections, right?
Yeah.
And so if you make them too fine, what's the problem with that?
It's just a cylinder.
Yeah, it's just, right, I mean, they're gonna break off then, right? I mean, when we apply a shear force to those, they're just gonna break off at the base, right? So we wanna get something that's husky enough that, you know, it's gonna be able to withstand some force. Now, you do get the benefit of the finer the thread count, the more of those you get though too, right? Okay. But so what would be like for a metal screw or for a machine screw, what's a, I'm guessing like 24 threads per inch or
How
50
big
threads
is the
per inch.
bolt?
Let's make it well, okay, so if we're gonna pull boards together, well, no, we won't even do that. We'll just say, okay, let's make it a big bolt. Let's make it a 1-inch bolt.
Fine thread is 12.
12? Okay, I think we can do more than that. That's fine, considered fine thread?
Yeah.
Okay, well, let's even do that one. So if we have 12 threads per inch, let's figure out what kind of mechanical advantage we can get on this. So didn't we do an example yesterday where we were gonna take a jack with a 1 meter handle and just see what kind of
Since
mechanical
12
advantage?
is common, or 12 is universal, but 14 is more common.
Okay, so we'll go 14. Okay, so
I don't know.
then
It's universal.
let's take.
Wasn't the 14 kind of more?
Yeah.
Universal.
Okay, so if we're gonna do, that's 14 threads per
Inch.
inch? Is that what the units are on that, Seth?
Yeah.
Well, that doesn't seem like that's that fine a thread, but oh well. Okay, so 14 threads per inch. So then that means we're gonna have to, if we've got, the distance between each thread would be what? Because that's what we're looking for here.
14th of an inch.
14th of an inch, right? So we've got to take 1/14 of an inch, and we're going to have to multiply by some changes here. We want this in metric units, right? Standard units. So what are we going to multiply by? We got to go from inches, isn't it 2.54 centimeters per inch? Isn't that right?
5.4 or 5.8?
I thought 5.4, but maybe I'm wrong. Somebody look it up.
It's 5.4.
It is 5.4, okay, so then we'd have 1 inch per 2.54 centimeters, and we'd want to go from centimeters to meters, right? So we'd multiply 1 meter divided by 100 centimeters, and then we're going to get the right units, aren't we? So we're going to get meters. So what's that give us for our value for P? Distance between threads.
A very small number.
Pretty small, yeah. Just give us out to like 3 sig figs, what do we get?
0.0017.
Okay, and we're saying the length of the handle is gonna be 1 meter, right? So then this is a pretty easy thing to do. So our ideal mechanical
Big
advantage
handles.
is equal to 2 pi times 1 over 0.00175. What's that give us for mechanical advantage?
A lot.
Would it just, give it to me,
3,590.
about 3590?
That-
That's
that
a
is-
darn big mechanical
That's a
advantage.
really big handle too.
Well, yeah, I mean, but if you wanted to jack up a house or something, you'd probably have that big a
I feel
handle,
like the
right?
handle might break before it's actually get pulled.
I mean, so even if you were talking about like, I mean, even if it were a terrible mechanical event, what if that thing were only 25% efficient?
That's so wild.
I mean, that's still a mechanical advantage of almost 1,000, right?
Yeah.
So every pound of force you apply, you'd get 1,000 pounds back. Now you'd have to turn that thing a whole bunch, right? To make that thing, if that's the ideal mechanical advantage, that is the ratio of how many turns you'd have to go. Like if I wanted to raise that thing, well, if I wanted to raise it 1 meter, I would have to push, I'd have to move that handle through 3,590 meters to make that happen, right? So you gotta really turn it a whole bunch. You gotta turn it 14 times to make it go up 1 inch, right? But,
That's not that much, 14 times.
I mean, no, it's not terrible. I mean, you can get the thing to move up
For that side.
quite a bit. Like if you, and that, I mean, that principle, well, I mean, so you see what I'm saying with that? So even if you're trying to figure out, like we looked at the example yesterday, I was talking to you guys about the trick of if you want to pull some things together, you know, if you take a screw and
Yeah, you
you
showed us that.
drill a hole that it'll pass through the hole, but the head catches on the hole, and you drill it into a piece of wood. I mean, even with wood screws, you know, which aren't, I mean, they're not really a very fine thread. You can get just enormous forces going on. So it's a pretty slick way to accomplish things that are far, far beyond our physical constraints, right? Okay. So one of you could easily jack up a house with that jack. Be no problem, right? I mean, like a big house.
Where's the fulcrum on the screwdriver?
The fulcrum, well, so it's right there.
Just right in the center.
It's right there, right? Because what you're really doing, if I look from above, here's how you can maybe see this. If you look from above, if this is, let's say that's the screw, or that's the cylinder that you're turning, and let's say here's the handle you're pushing on, right? So think about it this way. You're applying a force in this direction, right? And what are you really doing? You're applying a twisting force or a torque to this thing right there, aren't you? Right, see what I'm saying? Where is it pivoting? Right there. So you get this really large mechanical advantage because of that. It's not quite that simple because there's more than one thing going on here. You've got this ramp, but that's a way to conceptualize it at least, right? There's kind of an effective effort arm or resistance arm there that would be, it would be impacted by the pitch of the threads. Okay, but it's a number. I mean, you could figure out what it is, and it would effectively be someplace down here. Okay. All right. So that's a pretty impressive way to pick up very large things, you know, with a jack. It also allows you to make very, very fine adjustments, doesn't it? Right. Like if you look, like eventually, if you guys go into, a lot of you will probably go into physical sciences or engineering. If you want to make very precise alterations, like in college, one thing I can remember, one project we worked on, we were doing, my group, we had to build, well, we were doing some research with a certain type of a dye laser where you could adjust the frequencies, and so we had to get very, very precise optical alignment of the beams. And so to do that, we had to get this table moved up to where it was level to unbelievable precision. So what'd you do? Well, that. You had a really fine thread on the base that you could adjust with a long handle so you could move it through very, very small angles. And by moving this thing through a really small angle, you could move it on the order of, of microns, millionths of an inch, very, very easily, or millions of a meter, I mean, really precisely, right? So
How did you measure whether or not that was level?
whether or not it was level, but just by looking at the beam, you could, I mean, with light, the nice thing about light is, light shines in a straight line for any distance, and so you could shine it on a wall far away, and you could see, so you're greatly magnifying, like even a tiny angle is gonna move that beam a little bit, right? So you could get it lined up that way, where you get two beams coming onto the wall, and you could just make sure that they're lining up vertically. So, okay, so what else? So we talked about screws. Screw jack, there's just another picture of it. And you get an idea, it's kind of a little blurry, but you get an idea of what this looks like. See, it's just threaded through this metal, right? And so you can pick something up by setting a weight on top of this thread and then just twisting it, right? This threaded pipe. Okay, wheel and axle. Okay, wheel and axle, another one, very, very useful. So what's going on with the wheel and axle here? If I'm gonna wrap a string around, or a cord, or some kind of a line around what we're gonna call the axle, which has a small radius, right? The wheel has a larger radius, and we also have some kind of a line wrapped around the wheel in this case. Do you see that this is gonna create a mechanical advantage, right? This is just like a lever, isn't it, right? We could think about the spokes on a wheel, right? A wheel is just, if it's a solid wheel like this and a solid axle, it's just an infinite number of spokes essentially that are connecting to the center of the shaft, right? But really we could do this for a very small distance. We wouldn't even need a wheel and an axle. We could just use a lever and put a fulcrum in the middle, right? For example, let me draw a picture over the top of this. So let's say that we're gonna do this instead. We're gonna have this lever. There's my lever, and I'm gonna put a fulcrum right there, right? I could just attach this line to the end of the lever, couldn't I? And I could push down right there, and I'm gonna raise up that weight a little bit, correct? Right, everybody agree? That's a simple what class lever? First class lever, isn't it? Because the fulcrum's in the middle. So here's the input force, right? And here's the output force right here. I'm applying this output force up in that direction that's raising this weight, okay? Now, what's the problem with this if I actually use a lever? Kind of carry this through.
It only goes so far.
Well, it only goes so far. Once I start to tilt this thing a little bit, what happens?
Loses efficiency.
Well, it's going to lose efficiency, but you see what's going to happen. The lever, this weight's always going to hang down vertically, and so once this thing gets twisted a little bit, like let's look a little bit later after I've picked this thing up. Well, now what's going on? Now this weight is, there's my
Moves
weight,
it to the side.
right? Yeah, I don't get it's going to alter that angle a little bit, isn't it? Right? And so the forces are not acting perpendicular to the lever. We haven't talked about torque yet, but you see that would not be ideal, right? It's going to be harder to pick this thing up once it starts to become, once the forces start to be applied at an angle, right? When we talk about torque, that'll become clearer, and that's coming up. That's the next topic we'll hit is torque when we're done with simple machines. But one way to overcome that, to always keep the force perpendicular to the lever, would be to make the lever continuous. Just make it an axle, right? Because now when I twist this thing up, if I turn this wheel, where is the force being applied? Well, it's always being applied perpendicular to the effective lever, right? When the wheel rolls up, well, there's just another part of the wheel to take its place, right? Think of it as being like like I mentioned spokes before. We could just make a whole bunch of spokes if we wanted to, right? That's not very efficient. Instead of making a whole bunch of spokes, make an infinite number in the shape of a wheel, right? But it really is just a wheel. That's all it, I mean, a lever is really all this is a continuous lever, a wheel and axle, right? So when we apply these forces, to this end of the wheel, we're really just applying forces to the business end of the lever, right? To the effort, the input arm on the lever, right? Okay? So where might you see a wheel and axle?
Covered.
Yeah, car, right?
If
If you're driving out,
Really, all modes of transportation, aside from a boat.
well, I mean, even a boat, really, because the boat, when you turn a steering wheel on a boat, what are you doing? I mean, it's not attached to a wheel on the car, but you're still using the mechanical advantage of the large wheel to. And if you look at this, it's actually not like thinking of my boat. If you look at a boat, if you look at the way the steering column is connected to the rudder on the boat, because that's what you're turning is the rudder on the boat, just a series of cables, right? And so, I mean, they're attached, they're wound about, essentially, it's a little different, but essentially they're wound about the axle. There's a rod on there that's wound about the axle. And as you turn this thing, it's gonna compress one of these two cables that's gonna pull not compress, it's gonna pull one of the two cables that's going to offset the rudder either to the left or the right. It's just that, right? But you gotta pull pretty hard because you gotta overcome the friction in the lines. There's a lot of water pressure against that rudder when you're going pretty fast. And so that's why you have a big steering wheel, right? And there's probably also some power steering and probably some hydraulics going on too. But have you ever driven a really old car? Have you ever driven a really old car? It doesn't have power steering. I mean, I don't know.
93.
Yeah,
I have an
probably. The
87.
Jeep has power
No,
steering.
it does, yeah.
I have an 87.
So there's,
68 or 60.
okay, that would be right before power steering. So, I mean, like old cars, if you look at an old car, they're first of all, they're hard to steer, right? The power steering was all done by Armstrong back in those days. It wasn't very good. But, I mean, you gotta really turn pretty hard to get that thing to turn because how are you turning it? You're relying on you're providing all the power to move those tires that are in contact with the ground. They're made of rubber, right? So they're pretty sticky on the ground. And so steering wheels used to be bigger than they are now. Like if you look at an old truck or an old bus or something, the steering wheels are huge. And they'd have little handles on them where you could go like this. But that's because you needed a bigger mechanical advantage. But that's what it is, just a wheel and axle, right?
I think it's 59.
So cars are really
59?
cool.
That sounds probably about right, 59.
There were some 90s cars. In fact, there was a car in 2000s that didn't have power steering.
Really? I could see like a race car or something, maybe not having power steering because you want to feel the road and you don't really ever turn through big angles.
Yeah, now they make it so it simulates, like when they have power steering, like in a sporty car, they have it so artificial, like
It gives you. And I think, and that even happens with, like, most cars, even if you're driving down the freeway, I believe this is true. I know on good cars it is. The effective gear ratio changes with speed. So the faster you go, if you're going really fast, ideally, if you turn through a big angle with your steering wheel, do you really want the wheels turning very far?
No.
Because you never should turn the wheels beyond a certain angle, or you're gonna flip your car, right? So it actually gives you a mechanical disadvantage after a while, the steering. So like with really fast cars, you can control where you're going more precisely because you can turn through a bigger angle and have the wheels barely turn. And as you go slower, it'll change that. It'll change the effective mechanical advantage. Yeah. So where else in a car would you see a wheel and axle going on?
Is it with the wheels?
Yeah, with the wheels. And it is with the wheels, but now think about this.
But it's
So it's pretty clear here probably that the ideal mechanical advantage, if we look at this picture, let me get rid of all my chicken scratchings up there, but you could probably see right away, where did I put my pen? Right there, thank you. Thank you. If we look at the two radii, the big radius is the radius of the wheel, the small r is the radius of the axle, right? The mechanical advantage here, ideal mechanical advantage, is clearly going to be what? Just big R over little r, right? Right? Because you're getting a mechanical advantage theoretically if you have 4 times as big a radius on the wheel as the axle. Theoretically, you're going to get a mechanical advantage of 4 out of that, right? Okay, but you could do the opposite also.
Make it go a
right?
lot faster.
Yeah, you could, if you had an excess of force, like coming out of an internal combustion engine, where you're producing really high forces, right, when you explode the gas and turn the crankshaft, and you'd want to convert that into speed instead of force, right? You want to move the wheels through a larger distance every time, because you can push on the wheel with a lot of force, right? So you'd flip this around, and you'd drive the axle, and the wheel would provide the output force, right? And so if you look at a car, you look at the axle of a car, it's pretty small, compared to, the car probably yay big, right? So you're twisting this thing around. The axle is relatively small, and the wheel is much bigger, right? Because you have that extra force to spend to make the car go faster and more efficiently, right? So you can go both ways with it. You can have a mechanical advantage or a mechanical disadvantage, okay? All right. So you get the idea of wheel and axle. That's actually a pretty good picture, right? That's a simple wheel and axle. Now, is this really a wheel? Yeah, it is, because you're twisting it, it's attached in the center, you're twisting it in a circle, right? You just want to have a little, you want to have a handle that pivots freely, right? So you
Isn't
can
that a
just,
double wheel and axle? In that
well,
specific case?
I mean, not really, because this axle right here the axle is considered to be the part
Yeah, but
that you wrap the line around that's lifting the load or moving the load, right? And so really, this is the effective axle.
it's kind of like two wheels and one axle.
Yeah,
a
except
little bit.
because these are rigidly attached to each other,
It doesn't matter.
doesn't really matter, yeah. I mean, it would have made no difference if you would have had a bigger piece of wood and a bigger hole in it, right, okay? Only advantage this has is you reduce friction a little bit, okay? Okay, next one. Yeah, I would argue that if there's one thing you would ever want to have in your car, a simple machine you'd ever want to have to get yourself out of more binds than anything else, it would be a block and tackle. I'd say a pulley system is going to be, that's the easiest thing to take advantage of because it does so many good things for you. It multiplies forces, but it also changes directions, right? Like even if, so let's think about a pulley here. So if I were to, here's just a very simple pulley where it's just one fixed pulley, right? So the load is attached via a line and you're going to pull on the line on the other side. Okay, so what do you think the mechanical advantage is going to be for that thing? Ideally.
1 to 1.
It's one. Doesn't do anything, right? It's not multiplying your force at all. In fact, there's going to be some friction in the line and in the pulley mechanism, so you're probably going to get a mechanical advantage that's less than 1. So you're not multiplying your force at all. But what's the benefit?
Changing direction.
What do you mean by leverage?
So if you were holding the ceiling,
Mm-hmm.
you could get something to the ceiling without ever having to actually be up there.
Right.
So I mean,
So let's say I had a pulley up here and I want to lift a heavy thing up to this desk,
you have just the line attached to the heavy thing
right?
around the pulley to
Mhm.
either side, so you can stand up for the whole time
Oh.
and raise it without having.
So how much force do I have to exert on the line to pick it up?
Just as much.
I mean, how much work do I have to do with my muscles?
Just a second.
I'd argue I have to do none, because all I'd really have to do, I mean, maybe enough, but all I'd really have to do is just hang on the line, and I could use my body weight to pull that thing up, right? I don't have to do
It also
anything.
doesn't, the outgoing force has a lot more different directions you can go and it'll still go the same.
Exactly, yeah, so I can apply the force in a convenient way. Like, my center of mass is above the floor. It's convenient for me to have my center of mass above the floor most of the time, right? So all I'd have to do, if I want to pick this thing up,
Sit
is
down.
just use my body weight and just let gravity do all the work for me. I just hang on this thing, and my mass is going to pull me down, pull the object up, right? So pulleys, even if they don't do anything in terms of multiplying your force, they're extremely useful because they change the direction in which you're acting the force, in which you're applying the force, right? So what about something like this then? What if I've got, let's look at a situation like this now where I've got a movable pulley, right? So it's attached to the ceiling, maybe way up there, right? and I'm standing on a chair, and I'm picking up on the pulley like this, okay? The pulley is attached to, with a fixed line, is attached to a weight. What do you think the mechanical advantage is gonna be there?
None, one.
Two.
Show me, it's an integer number, so show me, give me the finger. No, don't give me the finger. Give me, raise a number of fingers to tell me,
We could still give you the finger, it'd be correct, possibly.
possibly, but that's frowned upon. Okay. Oh, okay. I'm seeing lots of correct answers. Two is right. Why'd you say 2, Cyrus? Okay, what do you suppose n represents? You're right. What does n represent here, do you think? Think about, let's do a free body diagram for a moment. We gotta go back to free, Ahmad loves free body diagrams. I wanna make sure we get one in today.
You know it.
Really wanted to do one.
You know it?
So if we're looking at, let's look at the forces acting on the pulley, because really, we're acting on the pulley, right? We're acting on the machine, and the machine is acting on the load, but we're acting on the machine, right? So what are the forces acting on the pulley if I just hold this thing steady like this? Let's say I'm going to suspend this. So there's the point that represents the body. Okay, what's the force acting down? And this has a mass of m. mg, sure. Okay, so there we get a downward force of mg. Okay, what are the forces acting upward?
You're pulling?
Okay, I'm pulling, but
So
now
normal.
the pulley, the pulley doesn't know who's pulling on it or all it knows is what's attached to the pulley. Say it again? Well, yeah, this is here, but what's, from the pulleys, the pulley knows there's a line pulling down that has a tension,
And there's 2
right?
lines going up.
And there's 2 lines going up, right? The tension in each line, we're gonna call it T, but they're gonna be equal, aren't they? Wouldn't it be impossible if this is a fairly good pulley that has low frictions, just for the sake of argument, let's say it has frictionless bearings, okay? Wouldn't it be impossible for the tension to be bigger in one of these lines than the other line? If it's a frictionless bearing? What would happen if this tension were bigger than that tension?
They would.
Yeah, it would adjust
equal out.
itself, wouldn't it? Because it can twist, it can turn freely, right? So it's always gonna twist to equalize the tension. Does that make sense? Right? So then I've got tension T and tension T pulling up, and so I've got something like that, don't I? Right? What do you think?
When did all of these become relevant in human history? And when did we start to use this?
That's a good question. I don't know, but I would think people would have used rudimentary pulleys a long time ago. I mean, I want to say that's got to be 4,000 years ago, maybe more. I would think.
Yeah, like the pyramids?
Yeah, probably, but anytime when people, if you use ships, I know that even very, very early ships, some boats would have used pulleys. I would think, yeah, I would think this is something people would have figured out. Wheels were tough to make though, so I don't know. They probably didn't use wheels at first. They probably used like
Bars.
grease, something you put grease on a rope and pull it over a smooth surface or something. But I mean, it still would be a pulley of sorts, right? So if we solve for T, why do we want to solve for T? What force are we applying? Tension. We're applying T because we're only holding one of those lines, right? So this is a pretty simple equation to solve. There's only one direction in which forces are acting, that's vertically. If this thing is at rest, which it is, let's say, if it's at rest, what's my equation of motion? The net force acting, well, we haven't used that, have we? We just said net force. Never mind, I gotta do this. We just said it this way. The y component of the net force is 0, right? But what are the positive contributors? Look at my free body diagram. Well, tell me you guys forgot all this stuff. How many? 2 of them though, right? So I get 2t pulling up, t plus t, minus mg equals 0, so what happens when we solve for t? mg over 2. What do you know, right? That's good. So what's our mechanical advantage? 2, right? Because look, the force we're applying is twice as big as the output force. I mean, excuse me, the output force is twice as big as the force we're applying, right? 2 times T equals mg, right? So mg is twice as big as the tension. Does that make sense? So, yeah, that's good. I mean, we're able to pick, using this setup right here, we can hoist this thing up only using half as much force as would be required to pick it up without the pulley system. Now, there's one disadvantage there. We didn't account for it.
Twice as much rope.
You have to pull twice as much rope, for sure. But something else is going on too. What's the, you see another practical disadvantage of this? Friction, sure, but even if we have a really good pulley that has very low friction, there's still something else there. Because we're not just picking up the load, what else are we picking up?
Pulley.
The pulley, right. So we do have to carry the weight of the pulley also, right? That's the disadvantage of a pulley system, is there's the movable pulley, you always have to support the weight of the movable pulley also, right? But that could be relatively small. But the nice thing about this is, we don't have to stop there, right? We could do something like this is what we call a block and tackle, because we've got a block that's movable, and then the tackle is what attaches to the fixed, something fixed, ceiling, let's say, right? So we've got movable pulleys. We've got 2 pulleys on both sides of this thing. And so look at the path that the cord's going to take. So we're supporting this movable pulley, and here's where the far end of the cord hooks on to the top, to the tackle, so that it's fixed. It hangs from that hook. And look what it does. It winds around the first pulley, winds around the first pulley on the top, winds around the second pulley on the bottom, around the first pulley on the top, and then that's where I pull this thing. Okay, what's the advantage of this?
Lots of force.
Yeah, now if we make the same free body diagram, right, the downward force is just mg, but what are the forces acting on the movable pulley this time? 4T, because there's 4 lines, right? So what's the mechanical advantage going to be there? 4. So it's easy to, what's our rule of thumb then? How are we going to calculate the mechanical advantage? Just by looking at a pulley system, how are we going to calculate the mechanical advantage? The number of lines supporting the load, right? This one doesn't count because it's not attached to the load, right? That's the input force line. But the number of lines attached to the load calculates the ideal mechanical advantage just like that, right? And the nice thing about that is, if we want to do, you could look at some pretty complicated, this is what a real block and tackle looks like right there. What's the mechanical advantage of that one? 4, right? What about that one?
3.
3, okay. What's that one? 1, that's not so good, right? What about that one? 2, right? 2. Now, is that one probably truly 2? What's wrong with that one? Can you tell me something else?
The angle's not.
The angle's not vertical. Yeah, right. And so remember when we talked about icicles breaking power lines, right? As this angle gets closer to 0 right here, right? As that angle gets closer to 0, it gets more and more inefficient, right? Because only the vertical component of the tension is supporting the load. There's some wasted horizontal component there. So to make this better, what would we do?
Move the pulleys closer to each other.
Move it over there so they hang more vertically, right? Yep.
If you moved it past the first, or to
What do you mean?
if you moved it more than right above it.
Well, that wouldn't be good. Then you'd still be changing the angles. You'd want to have those lines hanging vertically if you could. As close to vertical as you can.
You want the lines parallel?
Yep.
So it would be worse if they came to one side and then kind of met where it's.
I mean, it'd be slightly, but it's not a linear relationship even. It's a sinusoidal relationship. And so think about a sine curve. A sine curve, initially, there's very little, look at a sine graph, right? If you've had trig, this is a way to think about this. When you're up here at this part of the curve, if I move left or right a little bit, the y value doesn't change hardly at all, does it? Right? You see what I'm saying? So it really doesn't, as you get very, very close to vertical, those really slight changes in angle have very little difference. Make very little
When you get
impact.
farther away.
When you get further away, you get to that part of the curve where it's pretty aggressive, right? Small changes left or right, change the amplitude, change a lot, okay? All right, what about something like, I got some cool pictures here somewhere. I thought I did. Yeah, look at that one. Look at that. So what's the ideal mechanical advantage
That's
there?
a 6.
6, yeah. But look, when you got this movable pulley like this block, really, it's efficient to use a mechanism like this because you don't really add that much to the weight of the block by adding more lines, right? Still the same block. And that's a pretty heavy block.
How do you even get that to retract though? Like to go back down?
You'd have to put something heavy on it. Yeah.
What if you needed to go down, they reach that heavy thing?
So
You got
for tomorrow, we might have a little Friday football fun going on because I want you guys to try to, I'm gonna throw you an imaginary scenario and as a sample content. And then you gotta figure out a way to think your way out of this using physics.
Walter, I showed Bryce and we're just remember all of this.
There's lots of simple
He likes it
ways
when
you
we're
can find.
Yeah, I bet.
So isn't it a cinch function that determines char line hangings?
It's a
Hyperbolic?
hyperbolic sign, yeah. Yeah.
Just, I remember my calculus professor's always calling it cosh cinch. Or,
Yeah, which is, yeah, I mean, some people, that's called, those are catenaries, the shape we make, yeah, which is, then you're right, yeah, it is. When you want to look at the shape made by hanging lines, describe the hyperbolic trade functions, yeah. Okay. We're gonna talk a little more about a cool application of pulley blocks and tackles. There's one really cool way, something really cool. I'll record this.
You want to give us a cool physics lesson for like 5 minutes?
Not today. You guys are testing today.
Oh yeah, we're testing.